Hello, everyone. Thanks for coming to our talk. My name is Eduardo Berrocal, and I'm a software engineer at Intel. And I'm going to be co-presenting this with Keith Orsak from HPE. He's a master's talk technologist there. The talk is called The Challenges of Measuring Persistent Memory Performance. So both Keith and I, among others, we're members of the SNIA Solid State Storage Technical Working Group, and we're working to define a persistent memory performance test specification document, or PTS. This is still under development. The PTS is intended to set forth a standardized methodology for setting up, testing, and reporting of persistent memory performance. And it also lists reference test platforms that are made of commercially thread-available party servers, so to make it easy to test persistent memory technologies among different vendors. The PTS at the end is intended to allow application and storage professionals to design, integrate, and deploy architectures based on persistent memory. In this first part, I'll go over the persistent memory configuration and why this is important for the PTS. But before that, let's get a brief introduction to persistent memory. So what is persistent memory? Well, persistent memory for us here is a new class of storage, right? But it's more than that, because it's also memory, right? It sits on the memory controller and is accessible by the CPU directly through loads and stores instructions, right? So this is a game changer because of the extremely low latency that is achievable. This low latency allows us to reconsider some assumptions from the past. For example, access granularity, right? Do we need to access so much data in one chunk as we used to do, right, with traditional block devices? So a lot of these assumptions, right, that are built and the industry takes for granted to be able to hide the large latency from block devices might need to be reconsidered. And in this case, we need to reconsider it to be able to test persistent memory effectively. So there's different ways in which we can access or and configure our persistent memory. And here in this figure, we can see 4 modes, although only 3 are related to persistent memory. The first one, the number 1 here on the left, called traditional block I/O, is here just for our reference. I understand that there's more ways that we can access data in traditional block devices, but nevertheless, this is the most common. So I show it here for a reference. The first way that we can configure and use persistent memory is in a so-called sector mode. So here in the column 2, and this mode is intended for to retrofit and to be able to use persistent memory with legacy file systems and applications. These are file systems that don't check some metadata, and they rely, for correctness, they rely on write sector atomicity at the device level. Now, with persistent memory, the issue here is because it's memory, every single access is turned into memory copies. And memory copies are only guaranteed to be atomic up to 8 bytes in the x86 architecture. So in order to protect legacy file systems from corruption, this mode supports block atomicity, sector atomicity, but at the software level, implemented in the driver. So there is some performance considerations here. Then number 3 is Fstax mode. In this mode, there is not such protection. So this is intended for what we call persistent memory aware file systems that know that they are running on top of persistent memory. And these file systems are very commonly used today. And you can find, for example, XFS and X4 in Linux or NTFS in Windows. All this has been adapted to run on top of persistent memory. So the key here for Fstax mode is that we can access persistent memory directly by passing the file system thanks to using memory mapping. As we can see here, we see 2 access paths in number 3. The one on the right allows to memory map a chunk of persistent memory directly to the user space of the application and access this data directly. So that's the fastest path that we can have for our data. Of course, the traditional I/O path through read-write is still available there, so we can still call and go through the file system. But once to be aware that even though file systems are modified and prepared to run on persistent memory, that doesn't mean that applications will get sector atomicity. So the atomicity is still only maintained until 8 bytes. So application has to be aware of this. And finally, we have number 4, which is the Fstax mode. And in this mode, we simply map the whole persistent memory capacity as if it were just one big file to the application memory space. Now, there's really not much performance difference for what I can see between memory mapping in 3 and 4. And so I always prefer 3 because it gives us the flexibility of a file system. But nevertheless, 4 has its use cases, for example, where file systems are not allowed in the path, like in RDMA, at least currently. So you need to use persistent memory in the Fstax. So if we look into how all these configuration options look at the OS level and how they get exposed to the application, we can see something like this figure here. This is shown from the perspective of a Linux file system, but it's very similar in Windows. So what we have first is at the bottom, persistent memory is configured in regions, which can be either single module or multiple modules interleaved. Then out of these regions, we can carve some space using namespaces. And these namespaces there's different types of namespaces, and here's where we configure the different modes that we have been talking about. So for example, we have in the column 2, we have the sector namespace, which allows to have that sector atomicity protection that I talked about. And so that creates a special block device called /dev/PM+CS. So as you can see, there's like that little S at the end that tells us that there's that sector protection. Then we have the Fstax in the middle, create the PM0, PM2. And then finally for the DAX, we just have the /dev/DAX. So as you can see, persistent memory configuration doesn't change a lot. You know, there's a lot of things that normal developers and users are familiar with. Once we have, you know, those block devices, then configuration is very similar to, you know, to how you will configure any other block device in the system. Or you can even do multiple partitions with multiple file systems and all that. Now, one thing to have in common, and the reason why this is important for the PTS, is because every single option here have performance implications, right? So it's very important for us to have a way to document all these configuration parameters very precisely to when we are reporting persistent memory performance numbers. So if you want to learn more, we have a white paper that we published last year. You can find the link at the left there. And the PTS itself, which although it's still a work in progress, we plan to release it by the summer. So again, when that happens, we welcome feedback as well. And now we are jumping into the second part with Keith. So Keith.
Thank you, Eduardo. Now we dive into challenges and methodology of testing persistent memory performance for the solid state storage performance test specification and touch on a few examples. Challenges introduced when evaluating persistent memory performance can differ from those of more traditional storage devices, such as hard disk drives or NAND flash-based SSDs. Persistent memory isn't mechanically limited like hard disk drives, nor does it have challenges with deterministic performance due to write hysteresis and background processes like flash-based SSDs. Performance for today's persistent memory devices is relatively deterministic when it comes to the raw device itself. However, other processes and management features within the configuration can create unexpected impacts to performance. For example, a server's power configuration can dynamically modify power for components and buses, bottlenecking performance unexpectedly when running a benchmark. Also, memory bus speeds can change depending on how persistent memory is configured within the server's DIMM slots. Software can also impact performance along the data path. File systems, I/O engines, and access modes can introduce seemingly unexpected performance impacts depending on how efficient they are and whether they store data direct to the persistent memory device or store it to a cache such as a system memory. Documenting these details is important when running a performance evaluation on persistent memory, especially if the results are to be recreated and/or compared. In the Solid State Storage Technical Working Group, we have worked to standardize the test process and shed light on such challenges. Our test specification starts with the reference test platform based on commercially available hardware and software which supports persistent memory. This is intended to normalize persistent memory performance measurements. It also sets forth the minimum hardware and software requirements for the proper usage of persistent memory storage, including associated best practices and settings for conducting, obtaining, and reporting persistent memory storage performance. Setup of the persistent memory device features can also be challenging and must be understood by the user, otherwise the relative test results may be unexpected and inconsistent. To alleviate this, we have detailed the most prominent features and functional settings such as module interleaving, access modes, and namespace configurations to educate users. This also helps determine which options best meet application needs. After the system and hardware is properly configured, the next challenge is deciding which workload types to focus on for the performance measurements. Traditional hard disk drive and SSD testing has focused on block I/O testing and demand intensity settings based on thread count and queue depth. Persistent memory storage testing differs in a few different areas. It focuses on byte-addressable loads and stores as opposed to block I/O. Persistent memory aware drivers translate OS level reads and writes into the loads and stores, and queue depths are transferred to thread count, such that the cumulative outstanding I/O is comprised of the thread count. In the persistent memory PTS, there are multiple test types to cover a wide array of objectives when evaluating persistent memory performance from synthetic to real-world workloads. Some engineers may just want to validate the manufacturer's performance specs, in which a simple synthetic benchmark would suffice. Other users may want to perform more complex evaluations based on real-world workloads for application optimization or storage validation. Recommendations for test type based on objectives are made to help guide engineers when determining which one best meets their needs. In addition to this, best practices for configuring the appropriate test and running it are defined as well. Each test type includes guidance on how to properly precondition in order to measure data in a consistent and reproducible manner. This leads us to our reporting requirements. Without a well-defined test procedure and reporting template, the data can lack substance. For example, the data may be seen as just a number if not well-defined. Also, it is not comparable unless there are similar results to compare to. Results can also vary widely or be difficult to interpret. The persistent memory PTS reports provide uniform and consistent reporting of persistent memory performance and list required information relative to configuration, workload, and results, as shown in the example on this slide. The report header lists critical administrative test information relative to test platform, device under test, setup parameters, and test parameters. This enables a standard audience to effectively review the results, and if necessary, attempt to reproduce the data with the comparable configuration. Now we will review a few graphical representations of test workloads evaluated by the Solid State Storage Technical Working Group. The graphical representation on this slide depicts a thread count sweep comparing I/O engines. For each I/O engine, there's a common trend as thread count increases. The IOPS increase until a saturation point is reached, after which the data series shows a knee-like characteristic in which latency increases and IOPS degrade. The knee helps the engineer pinpoint the optimal workload bounds for each I/O engine. It also shows how drastically I/O engines can impact performance and why selecting the appropriate I/O engine is important. This example on this slide is a graphical representation of a replay from a retail web portal application workload. In the graphic, you can see how performance, outstanding I/O, and latency trends over time. The x-axis represents time. IOPS are shown in the blue data series and represented by the primary y-axis. Latency is shown in the orange data series and tied to the secondary y-axis. Lastly, outstanding I/O is shown in the black data series and tied to the tertiary y-axis. There are a couple of significant trends shown in this chart. The workload changes drastically about a third of the way through the measurement, where outstanding I/O starts to increase and becomes less stable, peaking regularly. Then a potential bottleneck is revealed as both latency and outstanding I/O peak, and the IOPS plummet roughly 3/4 of the way into the measurement. Now we move to an example of a thread count sweep test of a single synthetic 64-byte random write I/O stream. We see a similar trend as the SNIA in the I/O engine example relative to the performance peaking out at a specific trend at a specific thread count and then continually degrading as the thread count increases. This is represented in 4 different graphics based on time, thread count, throughput, and total outstanding I/O. Each provides a unique perspective to dig deeper into the efficiencies of OS Sync I/O engine for this configuration. Lastly, this is an example of an individual streams test taken from a complex real-world workload of over 5,000 streams. The top 9 threads relative to IOPS were selected for evaluation. Each of the 9 individual streams is evaluated separately for 5 minutes. In the top 2 charts, the data shows relatively steady performance for each stream throughout their relative 5-minute measurement period. The bottom charts focus on multiple latency aspects consisting of average latency, percentile latency, and maximum latency throughout the 45-minute evaluation. These charts can help the observer pinpoint quality of service limitations within their application. IOPS are added to the last chart on the bottom right. This can add context around the latency distribution. For example, an IOPS threshold could have been exceeded, which caused overhead in which a slower data path must be utilized to service the I/O payload. This could cause a separation between average and percentile latency, and also increase maximum latency depending on the situation. This concludes our presentation on the challenges of measuring persistent memory performance and some examples of how the persistent memory performance test specification can eliminate those challenges. The PTS is targeted for public review this summer, so your feedback and involvement is greatly appreciated. Also, if you are interested in joining the Solid State Storage Technical Working Group, please feel free to contact us at askcsmi@snia.org. Thank you for your time.